So we're working with the standard normal distribution. Oh, in my experience, it helps to see this stuff drawn out as well as to actually hear the explanation. So we're going to use this program here, which will allow me to draw on the screen and talk through it while you're watching. Okay, so let's start with a basic probability question for the normal distribution, such as the probability that the z-score will be between -1 and +1. Now, what that translates to in terms of the picture is, again, this is the standard normal distribution. So that means that the mean is 0 and the standard deviation is 1. So each of these tick marks counts up by 1, or to the left counts down by 1. Again, the visual really helps here to get an idea of what we're dealing with. I started with a familiar problem, one that we've seen in the empirical rule, and therefore we saw it earlier in this lesson. But the idea then is that what we're doing is finding the area of this region between -1 and 1. Now, how do we do that? Well, this is where we go to the calculator or Excel, or there are a number of different statistical programs that can help you find probabilities for a normal distribution. I'm going to stick with the calculator and Excel versions because those are the technologies that we've been using. Again, there are lots of others out there. There are tables of values which we could use too, although they are much more cumbersome. So again, in the calculator, and there's the separate video for that, we're going to go to the command for normal CDF. Now, this command on the calculator allows us to set the lower and upper bounds, which is phenomenal. We start with the lower bound, which is simply -1, and then the upper bound, which is simply +1. Now, the default values for the mean and standard deviation are automatically programmed in, but it's always a good idea, I think, to include them anyway. And this will give us the answer, and it should be a familiar one since we saw it from the empirical rule. Now, please note there are going to be some more decimal places here. Now, the reason for this is that the empirical rule uses nicer values. In reality, it is actually a little bit more exact than that. But for all intents and purposes, 68% is what you can remember from the empirical rule. So that matches what we have here with that, slight variation. Let's try another one. Suppose we were asked to find the probability that the z-score is less than 0.25. So again, it really does help to have the picture here. Now, we will always label these tick marks along the axis. Now, in this case, the standard normal distribution has the quality that the z-score and the x values are exactly the same, so it's very easy to label it here. In the next lesson, we'll get to other distributions other instances of the normal distribution where the mean and standard deviation are not quite so nice. So 0.25 would be, 0.5 would be about there, 0.25 would be about here. So just a little bit to the right of center. And we're looking for the probability that z-score is less than 0.25. That's this entire region over here. Now, before we even do the calculation, we can already make something of a prediction as to what the value will be. See now, if it had been 0, everything to the left of 0 is 0.5. This includes a little bit of an extra space in there. So when we do get an answer for this, we should expect it to be a little bit bigger than 0.5. So once again, we turn to our technology. Now, in this case, we're not as fortunate as the previous one where we had a left bound and a right bound built in. You know, we had the -1 and the 1 built in right there. We could see them in our distribution as the left endpoint and the right endpoint, but we don't have that here. What we do have is a right endpoint, but we don't see a left one. And the reason is that this distribution, as much as it looks like it touches the axis, it's always just a teeny tiny bit above it. Now, it's such a minuscule amount that it's hardly, that we can't actually see it, but it is there. So we need to keep in mind that this is talking about going all the way out to -infinity. Now, we don't actually have the capability to type in -infinity on either the calculator or in Excel in such a way that the computer's going to understand it. So we get around that by using the scientific notation. And again, this is in the calculator and the Excel videos. -1e99. Remember, that's a -1 with 99 zeros behind it. Just 99 zeros. That's a massive number. So massive that it's essentially infinite as far as the calculator is concerned. At least it's about the largest number the calculator can actually manage. So that's our left endpoint. Our right endpoint, of course, is the 0.25. And then our standard normal distribution parameters, mean and standard deviation 0 and 1 respectively. We enter that in, and we get 0.598706, etc. 4 decimal places is a pretty acceptable standard for this. And sure enough, look at what we got. Something a little bit bigger than 0.5. Over time, with experience, you'll get used to the idea of just the size of the area that we're working with. It does help to draw the picture to see that, at least get a comparison as to whether it's, going to be around 0.5, a little bit higher, a little bit lower, if it's going to be tremendously larger than 0.5 or tremendously smaller. Let's look at a few other examples. This time, let's try something that's open-ended to the right. The probability that z is larger than 0.25. Now, you'll notice, first of all, that I use the exact same limiting value, but this time, we're looking at to the right of it. So it's going to look very similar, except this time we're looking at the other side. There's actually a couple of different ways to go about this. The kind of a traditional way, because we didn't always have technology available to us. There were other methods, as I mentioned before, like a table that had pre-calculated values. Somebody else had done all the legwork, and all you needed to do was look up the right value in the table by looking at the z-score and then going, oh, look, that's the probability. But those values were always based off of coming from the left towards the right. Finding an area like this section over here. We're not looking at that section anymore. We're looking at the right section. So one of the traditional ways is to realize that this actually is the complement of what we saw in the previous slide. So if we already know this, or if we can obtain that more easily for one reason or another, we can use the complement rule. Now that value was, we rounded it off, but 0.5987. And the complement of that then is 0.4013. A quick subtraction in your calculator will give you that. Now, just to verify that, and to do it, what probably most of you guys would do anyway, is to just go to the technology and use the Normalcdf. Now, in this case, we have to be careful. What we have here is the left endpoint of the region, and it's the right endpoint that extends forever to the right. So this time we need the calculator's version of infinity, but we need it positive because it's towards the right. And our usual standard normal distribution parameters. Again, I tend to lean very heavily towards the calculator for this, but certainly you can be using other forms of technology, Excel, numbers, etc. Oh, excuse me. Getting too close to the end there. So we get 0.40129, etc., which then rounds to 0.4013. So same answer either way. Again, it's not likely you would have this from the a previous problem so readily, but sometimes you do. Sometimes it's just easier to always work from the left and then use the complement rule, but in this day and age of technology, to be honest, most of us are probably going to just use this with the left and right endpoints. So let's do one more, because there is another interesting situation that may come up here. Now, one of the things to realize, and I'm just going to write this again for, this is not the problem we're doing, it's one we did all before, but it's something that I want to use for comparison here. This is actually an AND statement. This is the probability that -1 is less than z, and at the same time, z must also be less than 1. That's what keeps it in between them, because it has to be bigger than the -1, but it also has to be smaller than the +1. So, I mean, like 2, if z was 2, that would certainly be bigger than -1, but it wouldn't qualify for being less than 1. Occasionally, you see an OR statement, such as the probability that z is less than -0.5 or z is greater than 1.3. Now, in this case, a number cannot fit both of those at the same time, and it helps to, again, to see the picture. and see what regions we're looking at to really get that. So, negative 0.5 is here. 1.3 is about here-ish. And these don't have to be perfect. It's just meant to give us an idea of what we're looking at. And what we're looking at is, oh, excuse me, we're looking at the region to the left of negative 0.5, because that's where the z values are less than 0.5. And the area to the right of 1.3, because that area, or that region, is where the values are greater than 1.3. So you can see that these are disjoint or mutually exclusive. What that means is that we actually need to find the area of each region, the probability for each one, and then add them together as the addition rule does. So the probability that z is less than negative 0.5, or that z is greater than 1.3, actually has to be written as the probability that z is less than negative 0.5 plus the probability that z is greater than 1.3. So we need to find each of those regions separately. So for the probability that z is less than negative 0.5, we need our technology, Normalcdf. This one, again, this is the region that is extending outward to the left forever, so we need our calculator's version of negative infinity. And on the right side, we have negative 0.5. For the other probability, again, we need a separate calculation. This one has 1.3 on the left and extends to the right forever. So we need our positive infinity on that side. Oh, excuse me. And our mean and standard deviation. We get these values, and there we should be all set. Now, it's hard to estimate from this perhaps what we're going to get, because this first region off to the left here is definitely going to be less than 0.5 because it's further to the left than the center, right? So, but the one on the right is much, much smaller. So it's going to be hard to estimate this just based on that. But at least this helps us set up the two separate Normalcdf commands. So again, we go to our calculator. And for the left side, we'd get 0.3085, and that rounds down so it stays as it is. For the right side, oh, excuse me, I'm making all kinds of mistakes here on my calculator. We'll try that again. For the right side, we get 0.0968. And calculator or just quick arithmetic, 0.4053. Now, there is another way to do this, I suppose. And much like with the area to the right, what we can do is actually a complement. what we could do is find this area. And this is where the complement actually maybe perhaps starts to shine with the technology, because it's cumbersome to have to type these two separate commands in, get these two separate values, type those in and add them. Another alternative would be to find the area in between them and use the complement rule to find the remaining area. So let's take a look at that alternative. So again, the probability that that z is less than negative 0.5, or that z is greater than 1.3. What we can do is use the complement rule to say 1 minus the probability that z is between them. So again, here's our negative 0.5. Here's our 1.3 roughly. And what we'd be looking at here is, again, the area in between these two curves, or in between these two vertical lines. So in this case, we can get away with doing one normal CDF calculation, because there's only a single region to find the area of, from negative 0.5 to 1.3. And it has the added benefit of, since it's a completely interior region, we don't need to worry about that 1E99 thing for infinity. A single normal CDF calculation is quicker and easier than having to do two. And what we get out of this is 0.59466, which rounds off to 0.5947. So our complement rule then gives us 0.4053, which matches what we had in the previous example, or the previous version. So we can do it either way. I find it very, very helpful to use this drawing tool. I highly recommend that you draw out your own. I mean, I happen to have access to the technology to draw a picture of it, but you know, it doesn't have to be pretty. Draw your own. Just draw out a number line and then a bell-shaped curve. Don't worry about if it's perfect. Don't worry about if it's totally symmetric, and then throw down some tick marks. And again, don't worry about if they're properly placed or what have you. The idea is just to get a quick concept of what you're looking at, to give a visual aid that helps you define the left and right endpoints of the interval that you're finding the area of, and to kind of shade it in and maybe get an idea of the size of the area. You know, are you looking at something that's going to be very close to 1 because it's got almost all the area, or something that's going to be closer to 0 because it's a very narrow region, something that's going to be close to 0.5, you know? Just to give you an idea of what you're looking at, so you're not just typing buttons on a calculator and it's spitting out this meaningless number at you. It gives you something to hold on to so that you can actually understand what you're looking at. So yeah, I mean, it's a pretty simple thing. It will get a little bit more complicated as we go, but for now, it's a pretty simple little procedure.